Okay, so here is a problem that says the following. So, okay, another problem. Problem 2. Okay. The length L of an organism depends upon time. So L is the length, okay, depends on. So the length of an organism on time, T, on its density, okay, density, time, time like what, since it was born or something, an assimilation rate that I'm going to call it R, assimilation rate, assimilation of food, I guess, okay, not that they assimilate each other. Assimilation rate, okay, and they will tell us the measures, the units for these things, and on its resource use rate U, let's call it. So this is resource use rate. Okay, show that there is a physical law involving two dimensionless quantities. So in other words, they say the following. If we have the length of an organism modeled by a law that involves the length, the time, the density, the assimilation rate of food, and the resource use rate, so how fast they eat the food. So we're going to assume that this is true. Okay, then there are, how they say it, two dimensionless quantities that are sufficient to describe this physical law, that describe fully, if you want, this physical law, the physics of it. Physical law. Okay. All right. So this sounds to me a pure Buckingham Pi theorem that says the following. If you do the dimensional theory, then the number of independent variables in the linear system that turns out when you do the dimensional analysis. So the number of independent variables are sufficient. Those independent variables are sufficient to describe what is going on. So we will have choices in what are those dimensionless variables, but you know, the point is that there are just a fixed number of them, right? So it's how many independent variables they turn out from solving the linear system. All right, so first thing is first, decide, you know, what are the fundamental units for each of these things that is involved in the problem, and then, you know, kind of set up that linear system. So there you go. For L is L. For T is time. For R, they actually tell us what it is. What is it? Problem. Okay. So assimilation rate, mass per area per time, right? So it's mass per area. Oops. Mass per area. So it's over area per time, over time. Okay. And by the way, it's good to kind of keep track of the fundamental units. Okay. Fundamental units. Okay. So they're not always just mass, length, and time. Sometimes we have others. There is a table in your notes there, right? So That's the use of that table if we ever need it. Okay, and U, resource use rate, so it's mass per volume per time. So it's mass per volume, volume is length at -3, per time T at -1. Okay, so here the fundamental units that we have mass, we have length, and we have time. Okay, all right. This thing. All right, so now this being said, our law, let's call it law 1, okay? So from law 1, we deduce that the combination of these guys at different powers has to be 1, right? You know, so powers that show up have to be 0, so any number power 0 is 1. So we would get that we have that L at A, now we'll have many unknowns, so there are 5, right? Then T, okay, maybe I should, no, it's not. Then T at B, then M, L at -1, T at -1, C, then M, L at -3, T at -1, D, and then, okay, did I forget anyone? I forgot row. Let's put row in here. Okay, I won't stop the video, I'll just put it in there. So this is L, right? Length. T is T, right? And let's put row. Row is density, right? So density is mass per volume. Okay, there you go. Okay, so now I can correct this one. Okay. So this is now is the row one. M, L at -3, C. Now the next one, M, L at -1, T at -1, D. And finally, M, L at -3, T at -1, E. So all this stuff have to be like M at 0, L at 0, T at 0. Okay, so now again we combine them, so we get that actually I did it here, so there are no surprises. So it's L at power A minus 3C minus 2D minus 3E, then M at power C plus D plus E, and then T at power B minus D minus E has to be L at 0. Yeah, I switch M with L, doesn't matter. M at 0, T at 0. Okay, so you see how we're getting our wonderful linear system. Okay, that's 0, right? And then we have this guy, that's another 0, right? And then finally, this fellow will be 0 as well. So we get the linear system with 5 unknowns, 3 equations. Right there. Right there, the answer to the question is, you know. Okay, so we have A minus 3C. So what I'm doing, I'm collecting these things, right? Okay. So A minus 3C minus 2D minus 3E is 0. And then C plus D plus E is 0. And then B minus D minus E is 0, right? So here is the matrix A that would describe this linear system, right? 5 unknowns, I'll have 5 columns. 1, 0, so this is for A, this is for B, this is for C, this is for D, this is for E. Okay, 0, 0, 1, 1, 1, 0, 1, 0, minus 1, minus 1. Okay. And now we have M is the number of columns number of columns, okay, is the number of unknowns, okay, which in this case is 5 because we have A, B, C, D, E as unknowns. And then we have rank A, which is K. We have to compute it. However you want to compute it, it will turn out to be 3. Okay, so it's basically for this kind of matrices that are, you know, like have a higher number of columns than rows, right? The way to start for rank, right? It's would be, you know, other ways, whatever, row reduction. So I'm looking if I can find the 3 by 3 matrix, a square matrix, right? For each, the determinant is non-zero. So right there, if I know Kramer's rule, I can compute this one on the spot. So this would be 0 plus 0 plus 0. That's a diagonal. And then I'm doing minus. The other diagonal would be 0 here, 0 here. But then I have 1, right? So the determinant of this squarish thingy, 3 by 3, is non-zero, so the rank is 3 because that's the dimension of the square matrix that I could fit in, and it's just, that's one way to do it. I'm not saying, you know, that any other way is wrong or whatever. It's just how I'm compiling it. Okay, so this is rank on 8. So that means that by the Buckingham Pi theorem, by the Buckingham. I like writing Buckingham. Huh? It's nice. Pi theorem. Okay. F. Okay. The law. Let's just say the law. F of L T rho. What was R and U equals 0. May be written. Okay. As some f of pi 1, pi 2 equals 0, where pi 1 and pi 2 are dimensionless. Dimensionless is written with 1 L or 2? Dimensionless. 2. I was right. Good for me. Okay, so are dimensionless quantities. Like scalars. Formed by combinations. Okay. Formed by combinations. Okay. Of L, T, rho, R, and U. Now, I'm going to put this in between quotes. Really, what are those combinations? Okay, I mean, actually, we're done now with the problem in itself, but would be nice to actually see what pi 1 and pi 2 could be. Okay, why not? So, all right, this means that we have to solve the system. And also, you know, in this way, you understand, you know, better what this dimensional analysis is about, okay? So we had that system here, right? So let's call it system 3. I'm going to call it 3, I think, right? I don't have 1. Okay, I'm going to call it 2. So it's system 2, okay? Is this linear system. So we have to solve it. Now, because the, okay, maybe here I didn't conclude this one, right? So from here, we deduce that there are m minus k, 5 minus 3 equals 2 independent variables, okay? And then apply Pi theorem. All right, the point is that now we can solve that system. We'll have 2 independent variables, and then we're going to form the pi 1 and pi 2, the dimensionless quantities, okay? So let's see. All right, so for the, from 2, okay, we can solve it. All right. So yeah, okay. So 2 is like something like this. Now you can solve it as you wish. That's I'm rewriting 2 here actually. Okay. Okay. Good. All right. So there are 2 independent variables. Okay. I can choose whichever I want. Okay. Choose D and E. Okay. So these are the ones that will be independent. And then the system becomes A minus 3C equals 2D plus 3E, right? And then I'll have C equals D plus E. And then I'll have B equals, okay, here is a minus actually, right? Yep, okay, minus D plus E, where E plus D plus E, I repeat, they can be whatever they want. And then we solve this one, okay? And we end up with a solution of the form. So A will be minus D, so here, solve, okay? B is D plus E, C is minus D plus E, and then D is in R, and E is in R. So in this way, I can see the entire shebang together, all right? And now I have, right, a 2-dimensional space of solutions. So, you know, I'm not getting into the linear algebra. I'm gonna just say, okay, so what about if now I'm gonna say if D is 1 and E is 0, then I'm gonna get to have A is minus 1, B is 1, and C is minus 1, okay? And the other way around, if D is 0 and E is 1, right? So I'm taking the 2 directions in the span of the linear space, right? 2 independent directions in the linear space of solutions, okay? A is 0, B is 1, C is minus 1, fine. Okay, so we got these 2 solutions, and what these 2 solutions will give us a choice of those 2 non-dimensional variables that are sufficient to describe whatever is going on here. Okay, so I'll just write them on the next page. Okay, so we have A is minus 1, B is 1, C is minus 1, D is 1, and C is 0. So that's 1. And the other one was A is 0, B is 1, C is minus 1, D is 0, E is 1. And then we have L, T, rho, R, and U as variables. Okay. So now if we take combinations of these variables at these particular powers, that will give us a non-dimensional variable. Okay, so pi 1 is going to be L at minus 1, T at 1. Okay, this is a minus 1 here. Rho at minus 1, R at 1, and then U at 0. So in other words, pi 1 is going to be T R over L rho. Okay. What about pi 2? Pi 2 is going to be L at 0, T at 1, rho at minus 1, R at 0, U at 1. Okay. Okay. So pi 2 is going to be T U over rho. Okay. So by pi Buckingham Pi Theorem, we can conclude that, so let's say conclusion, okay, f of L, T, rho, R, and U equals 0 can be expressed in terms of two variables as a law, okay, can be expressed as f of f some function of these particular two non-dimensional variables. So the first one would be TR over L rho, so that's one, and then the other one TU over rho, okay, equals 0. Okay, can we say even more than that? Well, actually, I'm going to take this one on the next page because it's fun actually to maybe extract even more information. Like, okay, can we learn something from here besides the fact that we can reduce the number of variables, right? So there you go. That's it. Okay, so there is, that the length of an organism can be described by a physical law that includes these two particular adimensional variables that combine, whatever is getting into there. Fine. So, I can say, well, if I can actually say from here that this is an implicit relation, so I'll make it explicit. So I'm going to pull out, let's say, TR over L rho is some function, let's call it G of TU over rho, right? Okay, so so I can say, well, L then, I'm solving for L, right? And here would be like solving for TR over L rho. Okay, I put in the between quotes because it's not, but it's a process that we think we could do, right? But we don't know what F is, so we cannot, put our hand on it. But here, for L, yeah, we can say, okay, so L will be R times T over rho. There is a reason why I'm grouping it like this. And then some function, right? It would be over G, right? So, okay. So let's say some function little g. So it's over, right? So, okay, let's do it over. So, okay. It would be a TR over rho and then 1 over G. I'm doing this so you don't think I cannot do the algebra. So R T over rho and then some function. I'm going to call this one little g, right? Some U T over rho, and I'm grouping them like this because then, this becomes obvious that is the same quantity, okay? So can I deduce anything from here about how the length of an organism depends on its environment and whatever was there? So here for some function G that we don't know, okay? Well, what we can say is that the length of the organism, right? So we can say something like the length L of the organism in question, okay, or whatever we're doing there, depends directly on its, what was this called? I forgot what was this called. Resource assimilation rate. Okay. Assimilation rate. In other words, more food gathers, longer it is, right? And then also depends directly on the ratio, see, it's the ratio of time and density. Okay, I'm not sure how to think about this one. The point is that I cannot say that depends on time directly, because you see, this shows up as a ratio. So, you know, this ratio, for instance, can increase if the time increases or if the density decreases. So I have to take it together. That's my point. You know, I have to look at t and rho together as this ratio. Not, I cannot do it separately, right? So it's a kind of, you know, so the length will be higher if this ratio is higher. And then again, you know, it's a kind of unclear because we don't know what g function is. So g function might be 1 over that ratio. So we cannot say really if it's a direct proportionality or not. So I would say, so it depends, and also it depends on, okay? It depends on. So I wouldn't say directly because we don't know what that function g is. So there you go. That's second problem. Okay.